Hello. Snehinh, can you once check that if you are able to share the screen? Hello, am I audible?
Yes, you.
Yeah, I'm here.
Yeah, okay. Can you just check once if you're able to share the screen or not?
Yeah, that's what I'll do. Just give me a moment. Is it visible?
Yeah, it is.
Cool.
We'll start in 2 minutes.
Okay.
Okay, hello everyone. Welcome to the second session of day 3. So today we have Snehinh. He's a ISA alumnus again, and now he's currently pursuing his PhD in Australian National University. So he was a BMath and MMath from ISA Bangalore and ISA Kolkata respectively, and he has been topping the class as always. And so he will be today talking about p-adic numbers, and that's it. Over to you, Snehinh.
Hey everyone, thank you so much, Sanchan, for such a nice introduction. I'm Snehinh over here. Am I audible?
Yeah.
Yes, you.
Okay, perfect. So today my topic would be, as you can see, a strange world where what we might call smaller becomes larger and what might be larger in our world becomes smaller. It's the strange world of p-adic numbers. So today my goal is to introduce what p-adic numbers are, what p-adic norms are, and show some nice applications of them, and perhaps some results which which till date have no other proofs other than proofs using p-adic methods. Okay, so let's start. So we'll start with something very simple, the notion of distance. You have encountered distance from day-to-day life, like not just in mathematics and physics or even like day-to-day life as such. And you might think that the notion of distance is a very physical concept and might only be related to geometry. However, that is clearly not true, at least in mathematics. Think of all the times where you have used the properties of absolute value or divisibility or some other property uh, in which you measure or compare size of two objects and then try to comment on, well, whether some equation has a solution or whether you can do something in some stipulated amount of time or something like that. And at times that problem might not be geometric at all. It might be a very number theoretic problem or a combinatorial problem, and still you use the notion of distance. And as I said, like divisibility or absolute value, these are nothing but notions of size and distance. So in the first section, what we'll try to do is generalize this notion of distance to an arbitrary setting. That is a setting of an arbitrary set. What do we mean by distance on that set? So does anybody know what a good distance function must satisfy? Like any axioms or anything which you think it must satisfy? Could you just suggest a few things to me? So for me, a distance function is a function d from x cross x. So it's from pairs of elements of x, a set, to the non-negative real numbers. So that's what happens with the usual distance, like distance cannot be negative. So what should be some nice properties of this distance? Any suggestions? I'll wait for about 30 seconds or so.
Sir, the notion of symmetry.
Perfect. So the notion of symmetry must be there. So dxy should be equal to dyx.
And triangle inequality also.
Exactly. Triangle inequality should also be there. So could you explain what triangle inequality is in simple words, like without getting into the inequality, which we'll state in a while?
Sir, any side is greater than equals to the summation of two sides. Sorry, less than equals to.
Exactly. That's the statement. But triangle inequality in some sense says that distance should be the length of kind of the shortest path between 2 points. Now you might have different paths between these 2 points. The shortest path might not contain a specific point. Say x, y, z are 3 points, and the shortest path between x and y might not contain z. So then the distance between x and z plus the distance between y and z, both of them are permissible paths. That path is somewhat larger than the smallest path between x and y. And that's precisely triangle inequality. So as I mentioned, the distance should not be negative. And also it should not be like, if x and y are the same points, then the distance should be 0. And if they are not the same point, the distance should never be 0. Like there should be some distance between them. So in other words, dxy equal to 0 if and only if x is equal to y. This is the so-called positivity of distance. And as you said, there should be some symmetry. The distance between x and y should be the same as the distance between y and x. And finally, the triangle inequality, or in other words, like if x, y, z are 3 points, then dxz should not exceed the sum of dxy and dyz. And once we club all these properties together, we get the notion of a metric. So a function d from x cross x to r greater than or equal to 0 is called a metric if it satisfies these 3 axioms. And a set with a metric is called a metric space. A non-empty set with a metric is called a metric space. So here are a few examples which we have encountered regularly. Firstly, the rationals, the reals, or the complex numbers. I hope you are familiar with these notations, Q, R, and C. Q means the rationals, R means the real numbers, and C means the complex numbers. So these sets with the usual absolute value, and you'll just look at the difference of 2 points and look at that absolute value. That's precisely how we measure distance in the real line or in the complex plane or something like that. And very similarly, there are other notions of distances. For example, the Euclidean distance in R2, R3, etc. There are something called the taxi cab distance, and there are many other forms of distance which you might have encountered till date. We would not need a lot of these metric spaces, but what we are interested in is in an objects, or rather in sets, which also have some algebraic structure to it, like some addition or multiplication, and also a notion of distance. So let's go to that part now. Most of the distances above, like the ones on Q, R, and C, are on sets that have an inherent algebraic structure attached to them. They have addition, subtraction, multiplication, cancellation, and other properties. So we want to see how these algebraic operations interact with the notion of distance on these sets. Consider, for instance, the absolute value on R. So firstly, the easier thing is like distance is induced by this absolute value function, as we just saw a while back. And multiplication behaves very well with distance, with respect to this absolute value at least. So the absolute value of x times y is the same as the absolute value of x times the absolute value of y. Like these are properties which we have seen pretty frequently. And addition is basically the property of addition is given by triangle inequality in this case. And it says that the sum of absolute values, it always exceeds the absolute value of the sum. And that is just equivalent to the triangle inequality. And like this implies the triangle inequality, and the triangle inequality would imply this. And this is how the two things are. And well, I have not mentioned it over here, but what do you think happens with subtraction? It's nothing new. It would just be the same triangle inequality because the norm of -1 would always be equal to 1. So now we would like to generalize this notion of absolute value to a bit more complicated sets which have this notion of compatible addition, subtraction, multiplication, and cancellation, along with the identity 0 and 1, additive identity of 0 and multiplicative identity of 1. So if it satisfies these properties of addition, subtraction, multiplication, and cancellation, we'll call them domains. And we would define absolute values on domain to be functions, similar to the absolute value on reals or complex or rationals, which has a few nice properties. The properties being that, first of all, it's a function into the non-negative reals. Secondly, the absolute value of x is equal to 0 if and only if x is 0. That's what happens in like the reals as well. Like the only thing with absolute value 0 is 0 itself. Secondly, the multiplication, or rather the third property over here, even though it's the second one, we are also talking about non-negativity. So this is the third property. It says that product of absolute value and absolute value of product are the same. Once again, that's what happens in reals, complex, rationals. So it's fair to expect this to happen in our complicated structure as well. Finally, if you have a sum, it should, because we, at the end of the day, we are interested in something related to distances, it should satisfy this version of the triangle inequality. That is, the sum of absolute values should exceed the absolute value of the sum. Any such function on a domain X is called an absolute value. Now, this sits well with our usual absolute value on Z, Q, R, C. And also as an exercise, like the way we got distance on Q, R, and C was just use the usual absolute value and look at the difference of 2 points and then look at the absolute value of the difference. And we said that's a distance, a notion of, like, that's what makes X into a metric space. Can you prove that given any X, a domain defined as above, this absolute value of difference thing is still a metric, which makes X into a metric space? Of course, this is fairly easy to show, but it's fine. We would not look at it right now. Later on, please do try it out. That would be a good exercise. And here is just one small remark. At times I will, because absolute value is a big word, and well, at the end of the day, it measures some size. So I'll use the terms absolute values and norms interchangeably henceforth. So please don't get confused by that. If you are, feel free to stop me at any time and we can talk about it. So henceforth, let K be one of Q, R, C. And the first question to ask is, are there more absolute values on them? The answer is yes. Like, first of all, we already had the usual absolute value. And now I will give you a new absolute value, or rather infinitely many new absolute values on them by using a very simple trick. Just look at the usual absolute value and then take its cth power, where C is a real number between 0 and 1, 1 included, it's fine, it's the usual absolute value. We're not including 0 right now, but it should be between 0 and 1. Now, using the properties of the usual absolute value and some analysis, some inequalities, and Olympiad tricks perhaps, can you show that this is still an absolute value? In fact, it's easier to do it for C equal to half. Like that's perhaps way easier than the general case, but maybe you can try to show that it still is an absolute value. That is mod x to the power half is an absolute value. And now I ask you a question, what happens if c is greater than 1? Say, for example, c is 2. What happens over there? Could you give me a quick answer?
Well, like x plus y the whole square is not lesser than or equal to x squared plus y. Not necessarily.
Exactly. So x plus y whole square is not necessarily less than equal to x square plus y square. And that's precisely why it's no longer an absolute value, at least for c equal to 2. In fact, this somewhat similar things can help to show that if c is greater than 1, it is never an absolute value. You do get some contradictions. Like you have to be a bit careful while you're doing the computation, but it's not very hard.
Can you
Now
do
what
this by
happens?
induction?
Yep.
Can you do this by induction?
Unfortunately, not exactly, because over here, c is a real number.
Oh.
So usual induction is on integers or some discrete system usually, and real numbers are continuous. So, but you can use induction to prove for some values, and then using those values, you can prove it for arbitrary c. That's a possibility. Anyway, so if c was 0 over here, we would want the norm of 0 to be 0. And for non-zero things, the norm was non-zero, and we are taking the 0th power of that. That turns out to be 1. So this absolute value would collapse into something like mod x equal to 1 if x is not equal to 0 and 0 otherwise. That seems somewhat boring and artificial, perhaps. However, the good thing is that it is still an absolute value. Well, triangle inequality is trivially satisfied in this case, so is the product rule and the 0 rule. So, well, at least in this case, if x is a domain, that is, once again, something with addition, subtraction, multiplication, cancellation, and the two identities, then this turns out to be an absolute value. And this is called the trivial absolute value or the trivial norm. You don't need any other property on x other than it being a domain for this to be an absolute value. And well, now you would tell me, well, you did nothing interesting over here. You just constructed, you had the usual absolute value, somehow tweaked it a bit and said you have infinitely many absolute value. That's kind of cheating. And then you gave me another example of an absolute value, which was boring, inherently boring. So are there more interesting ones? It turns out, yes, there are quite a few other interesting ones on Q. And let's look at this huge family of interesting absolute value, one for each prime number p. So by the fundamental theorem of arithmetic, we get a function, the exponent of p function, which I guess most of you have encountered. Like given any non-zero integer input, you just factorize it into prime factors and then look at the exponent of this prime p in that number. So for example, Vt of 46 is just V2 of 2 times 23, that's just 1. V3 of 54 in a similar fashion is 3. Say V5 of 17 would be 0 because like there is no power of 5 dividing 17. So what are the properties of Vp? So can you just mention a few properties before I move to the next slide?
Vp of xy is Vp of x plus Vp.
Exactly. So just the prime factorization of x, y is the same as the prime factorization of x times the prime factorization of y. So the number of copies of p occurring in x, y is the same as the number of copies of p occurring in x plus the number of copies of p occurring in y. Nothing you can, like, you cannot just get a prime factor by the combination of the two just popping out of nowhere. That's not possible. And what about addition? What can we say about Vp x plus y?
That has to be greater than or equal to the Vp of x plus Vp. No.
It's actually a good thing that you didn't say equality. Like we cannot comment about equality in this case, but you're right. There is some greater than equal to involved. So suppose x is even and y is even. What can we say about x plus y?
Even
That will also be
That will also be even. So if 2 divides x and 2 divides y, then 2 has to divide x plus y. More generally, if 2 power k divides x and 2 power k also divides y, then 2 power k has to divide the sum. Using this idea and replacing 2 with another prime, any other prime for that matter, if p power k divides both x and y, then it should divide the sum as well. Hence, if x, y, x plus y, all of these are non-zero integers, then vp of x plus y has to be at least equal to the minimum of vpx and vpy, because vpx is greater than equal to the minimum, vpy is greater than equal to minimum, and using the argument above, that just means that the minimum, like vp of x plus y has to be greater than equal to the minimum. And this is very interesting, and actually this property is the whole reason why the topic of p-adic numbers, norms, and everything becomes interesting, as we will see in a while. But I said p-adic norms related to p. VP has nothing to do with the norm as of now. So how do we make VP into a norm? The idea is simple. You had a product becoming a sum, so you want to make that sum into a product again. And the way to make sums into product is taking exponents. So fix any positive constant, c less than 1, and consider mod xp is equal to c to the power vpx, if x is a non-zero integer. And it's again an absolute value, so we would want the norm to be 0 at 0. And that is also one of the primary reasons why we are assuming c is lesser than 1. Anyway, like avoiding that for a while. So we have defined a function on the integers, which is equal to c power vpx if x is non-zero, and it's 0 if x is 0. So the first property would translate into xyp is c to the power vpxy. That is equal to c power vpx plus vpy. And c to the power a plus b is the same as c to the power a times c power b. Hence, it turns out to be just the multiplication property. Now you might say that it's only for non-zero things. What about 0? Well, if x or y is 0, then both of these sides are 0 trivially, and hence again we have equality. So no matter if x, y is 0 or non-zero, we have this multiplication property. Once again, if x and y were 0, then we would have to do some like simple observation. But if x and y are non-zero and x plus y is also non-zero, then the second property would translate into mod of x plus y p is less than equal to, instead of the minimum, it becomes a maximum because c is less than 1. And it's less than equal to the maximum of mod xp, comma, mod yp. But well, the maximum of these two is obviously less than equal to the sum because these are non-negative quantities. The sum has to bound the maximum, and hence we have the triangle inequality as well. So mod p is an absolute value on z. That's what we wanted to show. And so now with respect to every prime p, we have a new absolute value. With respect to every prime, and given any c between 0 and 1, you have another absolute value. Like it's an infinite family of absolute values in some sense. And usually, like just to make a life simple, unless mentioned, we would just say that C is P inverse because we somehow want to retain our P in the definition and in the behavior, and we'll just define modern P to be P to the power minus Vpn if n is not equal to 0 and 0 otherwise. So, okay, before I go ahead, what would be the what is the value of 27 by 5 mod 3, like mod 3 in the sense absolute value 3. So the absolute value 3 of 27 by 5. So what I mean to say is that, like, if n was 20, okay, we have just talked about integers. So let's just do 27 now. What would be the absolute value of 27 if p was 3?
So 3.
Unfortunately, not. The VP is 3, you're right. But then we have to take the exponent.
C to the power 3, sorry.
C to the power 3, perfect. And as I said, if it's not mentioned, we'll assume
1 by
C
27.
itself.
1 by 27.
1
It's
by
1 by
27.
Perfect. It's 1 by 27. What would be the 3 absolute value of, say, 108?
One by 27 again.
It's 1 by 27 again. So the even factor or any other factor, 2 powers or 2 powers or 5 powers or 7 or anything else do not matter. We just look at the p factor and invert it. That's how you define it in some sense. And now if we want to extend this to the rationals, and if there was a reasonable extension, it should satisfy the product rule. And so we should have mod A by BP times mod BP is equal to mod AP. And that just says that mod A by BP is precisely equal to p to the power the absolute value of B minus that, sorry, p to the power VP of B minus VP of A. And this should precisely be a unique extension. If there was an extension, this is the only possibility. However, you still have to verify that this is an absolute value in Q. I won't do it, and that's an exercise for you. The proof isn't very hard. It would only use the properties of it being an absolute value in Z and what values it is taken. But yeah, you should verify this as well. This absolute value on Q, and also the one on Z for that matter, is called the p-adic absolute value in Q. And this is why p-adic, well, just wants to, like, this is how we'll make the prime p into an injective, and we just make it p-adic in some sense. And because this absolute value is related to the prime p, we'll call it p-adic. So if p was 2, we'll call it 2-adic, p was 3, 3-adic, so on. Now we have already found a few absolute values. And what is the property of this absolute value? Of course, it's an absolute value, and it has all those properties which we had for an absolute value over here. But it has something additional, right? Some additional property, which is precisely the first part of this inequality, that mod x plus yp is less than equal to max mod xp mod yp, instead of it being just less than equal to the sum. This inequality has a special name. It's called the ultrametric inequality. So triangle inequality is kind of the metric inequality, and this is stronger than that. Hence, we'll call it the ultrametric inequality. And it has some very neat applications. For example, let's just look at one over here. Given x1, comma dot 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 to xn in Q, if mod xn p is greater than mod xip for each I less than n, so xn has the greatest of p-adic absolute value among the other elements, I claim that the sum, and this is the p-adic absolute value, I'm so sorry for missing the subscript, but sum I xi modulus is equal to the p-adic value of, or the p-adic absolute value of xn. No more inequalities involved. Like if n was, like say n was 2, then this is kind of the triangle ultrametric inequality. But over here, I'm saying it's an equality, a strict equality. So how would you show something like this? Let's just work with 2 elements for that matter. The same proof kind of goes through for arbitrary elements. But I don't want an exact proof, but what would you do? Like, what's the idea behind this? What do you think?
Power of p in summation xi would be the power of p in xn, then that will force it to be greater than equals to, and then by the inequality you can get it to be an equality.
Okay, that's completely correct. Of course, we have to be a bit careful because the powers might occur in the denominators as well, but that doesn't affect the proof. And as you said so rightly, like as you said, you can also prove it like this, but just if you were given that a norm satisfies the ultrametric inequality, this result is still true, and you just use the ultrametric inequality twice. In the special case of p-adics, as you said, like say, for example, these were integers, then any other term in the sum has a higher power of p dividing it, and xn has the least power of p dividing it. So if you're looking at the sum, the other terms are kind of like a p power, very high power of p dividing it, and this leftover term is kind of the remainder after some things when you divide by that high power of p, and hence the power of p dividing the sum is the same as the power of p dividing this last term. That's also perfectly right for p-adic. And now, in a similar sense, like this is kind of the same result, even though I do give a proof later, maybe you can skip it. Using the p-adic norm, any triangle, so what is a triangle in Q? It would be like just a set of 3 points. Now, if they are degenerate, like if x is equal to y or y equal to z or something like that, then of course you can still call it a triangle, but that's a degenerate one. So we're not interested in that. But I claim that no matter if it's degenerate or not degenerate, this triangle is isosceles. So that means these three norms given over here, the distance between x and y and z, and z and x, at least two of them are equal. Indeed, without loss of generality, if say this distance between x and y is less than the distance between y and z, then mod x minus zp by the ultrametric inequality is less than equal to the maximum of mod x minus yp mod y minus zp. Now we already know what the maximum is in this case. It's the second term, because that's what we are assuming. And hence mod x minus zp is less than equal to mod y minus zp. And we also have this chain of inequalities that mod y minus xp is less than mod y minus zp. That's what we are assuming. And remember that mod of minus 1 is always 1 in an absolute value with respect to an absolute value. And this is less than equal to this maximum, just using the ultrametric inequality once again, because y minus x plus x minus z is y minus z. And now, if we look at this closely, just ignore the term after the bracket, I claim that this maximum has to be equal to the mod of x minus zp. How do I do that? I don't explain it over here, but the reason I don't explain it over here is because I wanted to get an answer from you all. So why do I say that it is actually equal to mod x minus zp? That's what I do in the next step, whatever happens after the bracket. I say the maximum is mod x minus zp. So if we look at this closely, this y minus x p has a norm less than y minus zp, and that is less than equal to the maximum of these two things. So I am just saying that the maximum of these two things is strictly greater than the norm of the first thing. So maximum of AB is greater than A. So what does that imply about the maximum?
It is the second term.
It has to be the second term, because it's greater than A and it's maximum. It has to be the second term. And that is why we are getting the other inequality. And so they must be equal. So every triangle is isosceles in this strange world. If P is not 2, there are instances of equilateral triangles as well. If P is equal to 2, of course, like, well, just think about it. Maybe I should not answer it right now. Okay, so till now we have seen that we have these absolute values in Q, the trivial absolute value, the boring one. By subscript U, as I mean the usual one, and then we take power lambda, where 0 less than lambda less than equal to 1. And we also have the p-adic ones for some, like you give me a C and then you have a p-adic. So now the natural question to ask over here is, are there more absolute values in this case? And the surprising answer is no. So these are the only absolute values on Q. This is Ostrowski's theorem. Of course, the proof's not very simple, but it's not very hard. It's kind of like just a repeated application and some properties of real numbers. Yeah, properties of real numbers, nothing to do with p-adic as of now, but we would not discuss that. And finally, we started with Z and ended with Q as of now. Can we go further? So can we go from Q to R? Are the p-adic absolute values on R? Or say p-adic even further, p-adic absolute values on C? So what is a p-adic? By p-adic, I just mean like it's an extension of the p-adic one on Q. The answer is, this time the answer is a yes. But the proof is way beyond the scope of this talk, and it uses very advanced math results and everything. Results which are usually covered towards into the second or third year of a math degree. So I would not be talking about it at all. However, it turns out that the absolute value on Q can be extended to C. And this is a theorem due to Chevalier, and that says that there is an absolute value, a p-adic absolute value in C, which restricts to the p-adic one on Q. That's the definition of it being an extension. And this extension still satisfies the ultrametric inequality and all other mentioned properties of the p-adic norm, like the product property, ultrametric property, then plus minus 1 being 1. Those are there already. And then you have these properties, the algebraic consequence, geometric consequence, as a consequence of the ultrametric inequality. So you do get quite a few values. And because R is a subset of C, and R is closed under addition, multiplication, subtraction, and everything, this absolute value also induces an absolute value on R. Once again, the proof is hard, but well, we would be needing this after some point. So that concludes the first part of our talk. Do you have any questions? I'll just wait for a few seconds and then move on to convergence and p-adic numbers.
I had a question. Like, if p-adic norms are specifically defined, can we construct a metric space out of that?
Yeah. Given any absolute value, you can construct a metric space from it, right? And that was this exercise. Not this one. Oh yeah, yeah. Give me any absolute value, I can give you a metric space from it. Just look at dxy equal to mod x minus y.
So
Does
the
that answer it?
space will be will be discrete, right?
The p-adic one?
Yeah, inherently discrete, without the extension to complex numbers.
Okay. Unfortunately, that's not the case. It's not a discrete thing. It's totally disconnected. Like if you know what that means, like there are no
Yeah.
connected. Yeah, but it's not discrete. The only discrete one is the trivial one. So a discrete thing is
Okay.
where like the single point is open, and in the p-adic case, the single point is not open.
Okay.
Yeah. Anyway, so that's a good question, and we can talk about it later as well once we are done. But it's not discrete, and even to of course, like it's not discrete in Z itself, so not in Q and not in R, C, anywhere. Like it's never discrete. Okay, so now let's talk about convergence and p-adic numbers. Most of what follows is somewhat complicated, at least for the category A people, because you might not have seen calculus. If you have seen it, it should not be that hard for you. However, I'll try to give you the motivation behind all this concept. And even if you're confused with some technicalities, it's fine. What's more interesting are the applications, and we would spend sufficient time on it. And there we would just need some basic properties of p-adic number. So put those properties in a black box, and well, you can move on to section 3 as well. Okay, so now I'll share a small story like from Q to R. So does anyone know how one goes from Q to R? Of course, there are many different ways, but
So by the convergence of Cauchy sequences. on Q.
Cauchy sequences. Okay, that's a very nice idea. So we'll talk about Cauchy sequences in a while. And do you know any other way? Rather the
Dead point
exercise.
path.
Yeah, Dedekind
Something
cuts.
called Dedekind cuts.
Exactly. So Dedekind cuts would also give you R from Q. And there are some other different ways as well. And those are a bit more complicated perhaps. But these are the two most standard ways. But no matter what method you use, the model is very simple, right? Q has a lot of gaps in between. So like even though Q seems like, okay, given two elements in Q, distinct elements, you can find infinitely many things to fill the gap between them. But these fillings would also have some gaps between them. So Q is not exactly a line. It's kind of a perforated line in some sense. So to fill this gap, we introduce the notion of either Cauchy sequences or Dedekind cuts, and you get what we really call the real numbers. And this filling of gaps is what we'll talk about next. So here is a way to do it. Of course, this is not a correct way and somewhat circular, but well, the philosophy is simple. Every rational number admits a decimal expansion of the form an minus 1 finitely many terms before the decimal and possibly infinitely many ones after the decimal. We can talk about this even in the world of rationals. And well, if you know convergence and things already, you know, like we can talk about series convergence even without metrics for that matter. And that's how you do it. And you just define real numbers to be arbitrary expansions of this form. Well, there is some bad things over there. First of all, why should a real number have a unique expansion of this form? Secondly, like, what do you mean by an arbitrary expansion? Is it a formal one? What are the properties of that? How do you get the addition and multiplication? You can be careful enough to define all those properties over here. However, uniqueness is a challenge, right? 0.999999999 equal to 1. That was already a challenge in the case of rationals. In fact, the challenge itself occurs only in the case of rationals. Real numbers which are not rationals would not have that challenge. I guess you might have already seen this before, but these are the only so the way to resolve it is that you look at, instead of looking at possibly finite ones, you make every expansion into an infinite one and then resolve it. But well, we would not do that, but this is a good motivation, right? Like you can just look at the decimal expansion and say that, okay, real numbers is anything with a decimal expansion. Once again, it's fairly roundabout to define something like that, and somehow circularly can cause some issues. But the pedantic analyst can argue that in a sense, well, every real number is just any sequence of rational numbers coming very close to it. Do some identification on these sequences and just say that, well, that's real. Real numbers in any sequence. It's just a sequence of rational numbers. Well, it's a good exercise, at least for those in undergraduate right now, to prove that this construction works. Just looking at decimal expansions and like minorly changing a few things, talking about convergence in a different way, and show that that is how you can go from Q to R. And that's a perfectly valid way to do it. You don't need to do like technically do Cauchy sequences and things. But okay, because we do not have that much freedom in our hand, we would have to talk about Cauchy sequences. Once again, for the people in category A, you can skip this part if it's seeming a bit confusing. Of course, it's very good to get exposed to these topics. It's fairly conceptual. And then maybe later on, when you're comfortable talking about these, you can revisit this thing. So firstly, we say a sequence of real numbers converges to a real number x if this sequence of differences, xn minus x modulus, becomes eventually small enough. It might be very big at the beginning, but if n is chosen to be large, it is smaller than epsilon. In other words, xn, the terms of the sequence, become progressively, it becomes closer to x. Of course, there might be finitely many outliers, and that's permitted, but by progressively, I just mean that eventually, in some sense. Okay. And in such a case, because xn's are getting closer to x, the gap between xn and xm when n and m are sufficiently large, that would also be pretty small, right? Because like xn is also very close to x, xm is also very close to x. So xn and xm should be close to each other. Well, that should be the case, and that follows from the triangle inequality. So maybe this xn minus xm being very close to each other for sufficiently large n and m is this notion of convergence as well. It's maybe not converging to a specific real, but it is somehow like this is a converging sequence in some world. And this weaker notion of convergence is what we'll talk about, because this is a very good notion. You do not need to talk about the limit. The limit is basically this element x where everything's converging eventually. And we do not need to talk about where the things are going. We just care about the sequence and it being intrinsically close to each other, and the terms of the sequence being intrinsically like being close to each other eventually. So that's what we are bothered about. And that's precisely the definition of a Cauchy sequence in a domain with a norm. Of course, the same definition is valid for arbitrary metric spaces. We could have talked about it, but we don't need to. So it's fine. So a Cauchy sequence is something, a sequence of elements in the domain X, such that for any epsilon greater than 0 real number, there is a natural number n greater than or equal to 1 large enough such that the gap between xn and xm is less than epsilon. So xn and xm are very close whenever n and m are greater than or equal to n. And that is precisely like it being eventually close, like the sequence eventually becoming close, the terms of the sequence being close to each other. And this is the notion of a Cauchy sequence. As you can see in the definition, there's no mention of that x or any limit of any kind. Like it's a definition of the sequence in a very intrinsic fashion. So here are a few basic observations about Cauchy sequences. Every convergent sequence is Cauchy. Well, it's becoming close to that x, hence it's becoming like the terms are also getting closer to each other. Just use the triangle inequality. The term-wise sum and product of Cauchy sequences are Cauchy again. This requires a proof, but well, it turns out it's fine. And if x equal to r and we are looking at the usual absolute value, the funny thing is that every Cauchy sequence is convergent. So this intrinsic notion somehow gives us the limit, at least for r. Unfortunately, that's not true for the rationals. It's only true for the reals. Okay, so finally, for any real number x, I claim that there is a Cauchy sequence of rational numbers converging to that real number x. And I have described it over here. You just look at the partial decimal expansions. So the first one is whatever's on the left of the decimal point, like the ones, the tens and hundreds, and we just keep them as it is. But on the right, we include terms progressively. So first, we just look at till the first point after the decimal. So suppose we had pi, so we would look at 3.1 as the first term. The next would be 3.14, then 3.141, and so on and so forth. These are rational numbers. We already know that. And after every step, the gap between, say, pi and these numbers, that's becoming smaller and smaller and smaller, like, at a pretty fast rate, at an exponential rate, it's becoming smaller. You can verify that. Like if we are looking at the expansion till the nth space and then subtracting pi, so anything which is in the like difference would have at least a power of 1 by 10 power n plus 1. And that sum is lesser than 1 by 10 power n. Hence, you can actually show that this is a Cauchy sequence. Like whenever we have gaps going at exponential rate, it turns out to be a Cauchy sequence. And hence, every real number is, in a sense, a Cauchy sequence of rational numbers. However, there is, okay, here we have a few photos to explain the difference between convergent and Cauchy. So here is a sequence converging to 1. As you can see, like there might be a few outliers, but soon enough, everything is in this narrow band about 1. And that's basically the notion of a sequence converging to 1. 1 could have been replaced with any other number, maybe just replace 1 with an L, and then we just say that the notion of converging to L is precisely the terms eventually entering a narrow band around L. And a Cauchy sequence, even though this looks a bit too beautiful for an arbitrary sequence, but okay, it's basically, as you can see, like the terms are somehow getting closer and closer to each other as we are going further away in the n direction. We don't know whether they are converging or not, whether there is a line. For example, this thing might very well be equal to pi, and this all the terms might be rational. Then it does not converge in rationals, but it is still a Cauchy sequence. We can still talk about terms getting closer to each other. So that's the fundamental difference between a Cauchy sequence and a convergence sequence. Now there was, as I said, one may define R to be the set of all rational Cauchy sequences. The only caveat over here is that two Cauchy sequences with the same, there might be two Cauchy sequences with the same limit in R. Say, for example, 0.9, 0.99, 0.999 dot dot dot, and 1 itself.
Sorry to interrupt. There are two suggestions probably in chat. Should I read it for you? Or
Yeah, surely.
see that. Yeah, so Anhad says that if we take the sequence with the difference between terms are elements of harmonic series, the consecutive terms gets close, but the sequence clearly diverges. So he means the sequence 1, 1 plus half, 1 plus half plus half, 1/3, and so on.
Okay, that's a very good observation. Unfortunately, that's not a Cauchy sequence. The reason simple, because in a Cauchy sequence, you wanted this. Whenever n and m are greater than equal to n, it should be close. And over there, only the consecutive ones have small enough difference. Of course, you can say, okay, we'll take 3 up to 3 difference, up to 4 difference, and then it becomes small enough. But you start with, say, x5, and then you look at some x1000, and then the difference would be pretty big. And give me any element, I can find a bigger element such that the difference is huge. Hence, it's not a Cauchy sequence. Okay, any other questions inside?
There was one more comment, probably that's on the line of what you said now, that the terms don't have to be consecutive, the definition is stronger.
Yeah, the definition is way stronger. Exactly. So this is a strong definition. Like it's not just the consecutive terms, right? If you look at this diagram, anything after that point is close enough to, like, there is you can cut it off at some point, and everything after that is very close to each other. And that's what is needed in a Cauchy sequence. Is it clear now?
Yes, it's clear.
Yeah, I think we got it. Yeah.
Perfect.
Okay.
So now, as I said, like there might be two Cauchy sequences in R with the same limit: 1, 1, 1, 1, 1, 1, the constant one, and 1. And then you can look at 0.9, 0.99, 0.999, dot, dot, dot. So they should be treated the same. And how would you do that? Well, we'll introduce an equivalence relation and just say that two sequences are equivalent if, well, the difference is close enough to each other. And what do you mean by difference being close enough to each other? Differences being close enough to 0. Like them being close enough to each other is the same as the differences being close enough to 0. And that's precisely like using the notion of convergence. You'll say that two Cauchy sequences are equivalent if the difference xn minus yn converges to 0. Once you introduce this notion, it turns out that this equivalence relation is compatible with sum and product. Well, if there was a notion of limit, it should have been if these were convergent sequences. And using that, you can actually define R from Q, as was mentioned by someone, that R from Q can be constructed using Cauchy sequences. That's a good thing. And we would not be bothered to construct R from Q, but why did we talk about such so many new concepts, Cauchy sequence, convergent, completion, and so on? The usual absolute value was not the only absolute value in Q, right? We had defined a few more absolute values. So what happens if we look at the completion of Q with respect to the p-adic norm? We can still perform the same process. And what we get after doing this completion is, drum roll as well, the p-adic numbers. This is precisely the definition of the p-adic numbers. Of course, this is just a construction and it has some formal properties, but we should have some explicit examples as well. Like, what do p-adic numbers look like? For example, for real numbers, we know that it looks like some finitely many terms, a decimal point, and then a possibly infinite expansion. That's how a real number looks like. You can look at real numbers in different bases as well, but that's, well, at least this is one valid expansion. So we should have some explicit description of p-adic numbers as well. We'll have a look at it in a while. But now let's look at one example, a specific example of a p-adic number, which might boggle your mind. Okay, so now consider the p-adic norm and the sequence of numbers 1, 1 plus 3, 1 plus 3 plus 3 square, ... The consecutive differences over here are growing at an exponential rate. Like x1 is 1, x2 is 1 plus 3. So the difference is 3 for x2 minus x1. For x3 minus x2, the difference is 3 square, and so on and so forth. Unlike the case of a harmonic sum, if the growth is exponential and you look at the difference of these things, it turns out to be exponential, but in a decreasing fashion. It's 3 power minus n instead of 3 power n. It turns out this is a Cauchy sequence. So in the real case, this series seems to be diverging to infinity. However, with respect to p-adic norm, as the differences are well behaved, you can verify it's a Cauchy sequence. And so this must be a p-adic number. So now, does that mean infinity is a p-adic number? And that is not a good thing, right? Infinity being a number. And we wanted a subtraction and everything in a domain. It is not infinity in this case. But if you just do a geometric sum of 1 plus 3 square and so on and so forth, assuming it existed, in the real case, it does not exist. But in the p-adic case, as we showed, it does exist. This is a convergent thingy. This sum turns out to be minus 1 by 2. And so what you have in the world of p-adic numbers is that 1 plus 3 square plus ... is equal to minus half. Okay, I'm not joking with you. This is exactly what you have. And that is why some people are not a huge fan of p-adic, because they think they are ridiculous. How can something like this even make sense? But yeah, at least in number theory, it's one of the most important concepts these days. And even though it's reminiscent of something a bit more ridiculous, once again, this also has an interpretation, but a bit more ridiculous, like 1 plus 2 plus 3 ... equal to minus 1 by 12. This is actually valid in a very explicit format using the P3 norm, because mod 3 power n3 decreases rapidly. We actually can show that this sum converges, and it converges to minus half. So the moral of the story over here is that in the world of p-adics, there is no notion of greater than, lesser than, or of course you can talk about it, but it's not sensible to talk about such things, because sums and everything might not, finite sums might, but infinite sums might not respect greater than or less than. And we are not interested in that. So sign, rationality, all these things, they are just thrown out of the window. Oh yeah. And here are a few other crazy sums. The first one is in a similar spirit for the p-adics, 1 plus 2 plus 2 square. That turns out to be minus 1. So you might have seen some p-adic talks introducing this concept of infinity is equal to minus 1. And that's what they mean by when they say infinity equal to minus 1, they want to kind of give you a clickbait to see this thing. But okay, it's fine. The second one is a bit more interesting and harder to prove, but 2 by 1 plus 2 square by 2 plus ... These are all rational numbers. We can add them in the p-adic sense, the p-adic sense. It turns out to be 0. Okay, and now here is a small exercise for you. What can you say about the sum 1 plus 2 times 5 plus 1 times 5 square plus 2 times 5 cube plus ... This has to converge once again, because it is a Cauchy sequence. This can be verified with respect to the p-adic norm. Now, what is this sum? So can anyone tell me quickly, and maybe you can wait for a few seconds before moving on. So just call this x. And if we look at phi squared times x, that's everything except the first two terms. And that's how you define the geometric sum, right? You just do that, take the difference, and you get 1 minus 5 squared times x is equal to 11. So x is minus 11 by 24. Anyway, you can do some similar tricks whenever you have something like eventually periodic or periodic. You can use a similar trick and just do eliminations. Now for some more fun, consider p-adics again. And those who are familiar with, those of you who are familiar with some basic number theory can show that 7 is a square modulo every power of 3. Even though 7 is not an integer square, it's a square modulo every power of 3. I do give some instances. 7 is 1 square mod 3, of course. 7 is 4 square, which is 16 mod 9. And 7 is 13 square, which is 169 mod 27. You have to verify that, but it does work. So you do get things. And in fact, what you have to show using induction, in this case, you need induction, is that there is always a unique element xn from 1 to 3 power n, such that 3 divides xn minus 1, and xn square is congruent to 7 mod 3 power n. And then it's not very hard to show that this xn is a Cauchy sequence with respect to the 3 norm. And where does it converge? Well, as you can guess, like everything it's like progressively approximating the square root of 7. And we said there is no reason for signs to be preserved or anything, and the sign is just an like it's a construct by us to talk about real numbers in a better way. Other than that, it has no other importance. So your guess, if your guess this is right, that this approximates one of the square roots of 7, the plus or the minus 1. It doesn't matter. It approximates the square root of 7. And as we'll see soon, you can also construct complex numbers using this p-adic technique. Of course, like you might have realized it over here as well. Like instead of starting with 7, you could have started with -2 and then the same trick, and you would have gotten a complex number. Anyway, so now we'll talk about this p-adic expansion. One of the main importance of decimal expansion is that it allows us to talk about real numbers as a string of digits. We hope to do the same with p-adic. Over there, 10 power minus n rapidly decrease to 0. Over here instead, p power minus n does not decrease to 0, but p power n, the actual nth power, decreases to 0. That's why all these bad things are happening. Hence, to define the p-adic expansion, it should be in the opposite direction. That is, let's call it the p-adic point instead of the decimal point now. You have the p-adic point. There should be finitely many terms on the right side of it. And on the left side, there can be infinitely many points. And the expansion is precisely done in a similar fashion as before. And you assume these AIs are between 0 to p minus 1. That's how you used to write digits. It turns out this is a valid p-adic number. And that's how you write p-adic numbers in general. And this can be compared to base p expansion in the usual case, but over there, like you have the base p point, and then you go infinitely on the right side, and always finitely on the left side, possibly infinitely on the right side. Over here, the directions are flipped because the size of p is smaller than the size of 1, and so on and so forth.
Sorry to interrupt. There's one more question in chat.
Okay.
So Nilab asks, what justifies using the GP sum to evaluate the expressions? Does the algebraic derivation still make sense for p-adics?
It does, right? So that's the thing. When you're talking about GP sum, like you have to talk about convergence, as we talked about convergence a while back, and then you just look at the term differences, like -1, and then you look at the term -half or whatever we had. Just look at the term difference and show that with every term, the p-adic norm is decreasing. And that's decreasing exponentially. And that's how you define convergence. And you can use it to show that actually, like in the convergence sense, like the definition which I had given a while back, the sum 1 plus 3 plus 3 square, you take the partial sums and then take the limit, it turns out to be equal to -half. I guess that answers your question.
Yeah, I think got it.
Perfect. Okay, so now this is the so-called p-adic expansion. And as we had shown that 1 plus 3 plus 3 squared, that's precisely the p-adic expansion corresponding to this, like the p-adic expansion corresponding to 1 plus 3 plus 3 squared is this 1, 1, 1, 1, 1, and infinitely on the left side. And the subscript 3 still denotes base 3 or p-adic 3-adics. And we have just established that this is equal to minus half. And the 1 to 1, 2 thing is equal to minus 11 by 24. A good exercise over here is to find the expansion of root 7 in 3-adics or root minus 1 in 5-adics and show that at least till a reasonable level, that's not repeating. We know that in the real case, a decimal expansion is eventually periodic if and only if it's rational. These two things are not rational. And hence, well, you can actually show that they would not have periodic expansions, periodic p-adic expansion, eventually periodic p-adic expansions. Now, the set of all p-adic numbers is denoted by QP. And for the main theorem without a proof, every p-adic admits one and only one p-adic expansion. Instead of like in the real case, you had two expansions and things like that. In the p-adic case, you wouldn't have something like that. Everything admits a unique p-adic expansion. And that's a very interesting thing. Like now, a few properties of p-adic numbers, which we gloss through very quickly. First of all, every rational number is a p-adic number. Just look at the constant rational Cauchy sequence and then think of it as a p-adic number. The converse is also true. Like every p-adic number with eventually periodic expansion is rational, as I mentioned a while back. The p-adic numbers are a domain with operations compatible with operations in Q. So the sum of two rational numbers treated as p-adic numbers is the same as the sum of them as rational numbers, so on and so forth. Products, units, division, everything. It admits a notion of division by non-zero elements as well, just like the rationals. QP contains all the pth roots of unity. This is something new. So, well, nothing new to say, but yep, it does contain all the pth roots of unity. So you have to just a second. Okay, it does not contain all the pth roots of unity. It contains all the p minus 1th roots of unity. I'm so sorry, there is a typo over here. And I'll rectify that when I'm sharing my slides. So QP contains all the p minus 1th roots of unity. And hence, like, for example, I just mentioned that root minus 1 is in 5. Root minus 1 is the 4th root of unity. It is in the 5-adics. 3-adics don't have anything. In fact, they do not contain the pth roots of unity. They only contain the p minus 1th roots of unity. I'm so sorry for that. And QP admits a unique norm, a unique absolute value extending the p-adic norm on Q. It is still denoted by the p-adic norm symbol, and it satisfies the ultrametric inequality. And with respect to this norm, every Cauchy sequence in QP is convergent. This is a formal property of completions. And every p-adic number is the limit of a rational Cauchy sequence. So QP is somewhat like R, but with respect to the p-adic norm instead of the usual one. And now I mentioned the p-adic norm on QP. How would you define that? Given a non-zero p-adic number, consider its p-adic expansion. There are two possible cases. The p-adic point is involved or it's not involved. If it is involved, so you have a minus 1, a minus 2 up to a minus k on the right. And suppose a minus k is non-zero, the last non-zero term, then mod x is defined to be p power k. If it was rational, like if the left side stopped after some point or it's eventually periodic, you can verify that this definition works. And if on the other hand, the decimal point is not involved, so you have an plus 1, an plus 2 up to an, and then it stops and there are zeros after that, the p-adic norm is defined to be mod x, defined to be p power minus n. So it's kind of the same thing, but written in two ways because the decimal point might not be involved and the notation changes. But this is how you define. So if there are no decimal points involved, as you can observe, the p-adic norm is always less than or equal to 1. And that leads to a next definition, as we'll see in a while. But more generally, if you have xn going to x, a rational sequence converging to x in QP, the mod x in p, and x is a non-zero thing, then mod x in p eventually becomes constant, and that is precisely mod xp. You can actually prove that. Consequence of the ultrametric inequality. But okay, as I said, observe that anything which does not have the p-adic point involved has norm less than or equal to 1, then if we consider the set of all things which have norm less than equal to 1 and use the product property and also the ultrametric inequality, it turns out this is also a domain and it admits a norm because it's a subset of QP which admits a norm. This contains all the integers. Of course, any integer can be written as finite p-adic expansion, and you can show that it is contained over here. More generally, if a comma b are integers such that p does not divide b, then a by b, which is not an integer necessarily, is in the p-adic, is in ZP. And an element of QP is in ZP if and only if it is a limit of an integer Cauchy sequence. So in QP, everything was a rational Cauchy sequence. And in ZP, it's a limit of an integer Cauchy sequence with respect to the p-adic norms. So now the fun thing is we already said that a by b, for example, if you're looking at Z2, then 5 by 3 is in Z2. And I'm saying it's a limit of integer Cauchy sequences in Z3. Maybe you can try to find out what that sequence is. It's not very hard. We have already found out -half, so it shouldn't be very hard. You can do that. And every Cauchy sequence in ZP converges. And if we started with Z and its p-adic norm and performed the completion process like we did it for Q, you would get ZP. So these are some nice properties. And finally, as we observed, like anything where the p-adic point is not involved, it would have a norm less than equal to 1. And conversely, if the norm is less than equal to 1, then the way we have defined it, or we showed rather, we didn't define it, like the definition is otherwise, we showed that it is equal to that. If the decimal point is involved, then the p-adic norm is greater than 1, hence it's not there. So ZP are those elements where no decimal point is involved. Now, this ZP is called the domain of p-adic integers. It's a very important object and it has very nice properties. We would not mention all of them over here. But now, before we move to the applications, let's do just one final thing. Try to compute sums and products in p-adics. The fun thing is, till now you might have seen like a lot of theories happening and a lot of boring things are happening. But what's fun is that computations in p-adics are simple, just like the ones in real. If it was a real number or an integer, it's like just finitely many blocks and you do the carry over to the left and keep on doing it. That's precisely what you do for p-adics, for sums and products. Just one challenge, you have to do it infinitely many times. Of course, that's not possible humanly or even with a computer. So you just do it till you get tired and then right, okay, you do the product and that's what you get. At least that's a representative till some point. So let's do some computations. Consider the p-adic number x equal to, I'll call it from the right side. So it's 1, 2, 1, 2, 1, 2, 1, 2. And y is 2, 0, 1, 2, 0, 1, 2, 0, 1, dot, dot, dot. Now let us compute z equal to x plus y and w equal to x times y. For z, it's just you do the sum as I said. So as you can see, the units place, so-called units place, it's 1 and 2. You add them. And remember, we are doing base 3 kind of thingies. So 1 plus 2 becomes 3, which becomes 0 with the 1 carried over. Then the second is 1 plus 2 plus 0, which is again 3, which is 0 with the 1 carried over. And you just keep on doing it. Nothing new. And I can already see it somehow suggests that the patterns are repeating after some time. Like, okay, ignore these zeros, but 2, 2, 0, 1, 0, 0, 2, 2, 0. And you can actually show that what follows is 1 again, because it's 1, 1, and 2 over here. It would be a 2 over here. It's 1, and you can just actually verify that the pattern is repeating. Let's do the harder one, the multiplication. So how do you do multiplication usually? You just multiply this thing, the units place of the second one to the whole thing, write it down. Then you multiply the tens place and then write it down again, just shifted, and keep on doing that. Of course, this is not exactly the sum because you have to keep on doing it for a while. But at least for the first few digits, as you can see, like after some point, the first 3 digits, they would not be repeated. And like all of them would be 0 because we have shifted it sufficiently. The first 5 digits actually, in this case. So this is correct. And this one is at least till this point, it is what is happening. And you keep on doing it and you'll get the rest of the terms. I've not done it over here because, of course, I cannot just write some 14 or 15 rows and that would be boring for everyone. But at least this is how you do it, and you keep on doing this. This is not W, but this is approximately W. And now let's do some verifications. If you are not tired already, so if you have X and you look at X minus 9X, that's, as I said, 2, 1, 2, 1, 3 minus 2, 1, 2, 1, but with 0, 0 because you've shifted everything by 2 places. And that's a 7. And so X is minus 7 by 8. Similarly, Y is minus 11 by 26. The sum would be equal to minus 5 by 104 times 27. This 27 is nice. We had 3 zeros at the end, right? So that's what this 27 records. And now if you do the p-adic expansion of the second term, because there are no 3 in the denominator, this is precisely what you get. You can check out the working as well later on. But yeah, this is what you get. And thus z equal to x plus y should be equal to this thing, which is precisely what we had, right? That's good. Even x, y, it's easier to compute like this using rational forms. Of course, you can verify till 5th stage. Whatever we had is actually correct. Okay, now this is Hensel's lemma. We'll skip it for now. You can have a look at the slides later on. This is a quick diagram of how p-adic numbers actually look. So maybe I can zoom. I don't know. Okay, I cannot zoom over here. But as you can see, like first you divide it into like congruent to 1 mod 3. Those are the yellow loops. 0 mod 3, 1 mod 3, and 2 mod 3. What's the remainder when divided by 3? Then the green ones are what's the remainder when divided by 9. And for the 0, you can have either 0, 3, or 6. For 1, 1, 4, 7, and so on and so forth. And keep on doing that. And this is done till remainder mod 81 in this case. And then you just fill in those points. And as you can see, like everything has 9 points. There are 3 blue circle in every green, 3 green in every yellow, and 3 yellows. So 27 blue circles and 3 oranges in that. And each orange has 9. So that's some 243 elements over here. So that's 1 to 243, how it looks like in the p-adic world. The balls represent like how close they are to each other in some sense. Okay, now for the applications. Harmonic sums, already mentioned once in this talk by someone. So our first application would concern the harmonic sums hn equal to 1 plus half plus dot dot plus 1 by n. It is a standard exercise in real analysis to show that hn diverges to infinity in the usual sense. Actually, that's also one of the reasons why it's not a Cauchy sequence. Every Cauchy sequence is bounded, so it cannot diverge like that. And it's actually easy to prove that they are bounded. However, we would not do that. And what happens p-adically? That's what we are interested in. First of all, like what is hn p-adically? Are there any applications of hn and stuff? Now, before I proceed further, can you actually, can hn ever be integers? Of course, h1 is an integer, it's 1. But after h1, can it ever be an integer? What do you think? Because some of you might have seen this problem before. So say 1 plus half is 3 by 2. That's not an integer. 1 plus half plus 1/3 is 11 by 6. That's not an integer as well. So can this ever be an integer after 1? What's your guess?
It can.
It can't. That's the answer. And now that we know what p-adic numbers are, we'll give a very neat proof of that fact. This is the Thijsinger's theorem. It says that for n greater than or equal to hn is not an integer. Well, let's give a proof. Suppose k is the largest such that 2 power k is less than or equal to n. Because n is greater than or equal to 2, this k is greater than or equal to 1. At least 2 is there. So now you just look at the largest power of 2 less than or equal to n. Then 2 power k is a unique element in the set 1 to n with mod of 1 by x, the 2-adic norm of that is equal to 2 power k. Anything other than that would not have a power of, like it would not be divisible by a power of 2 greater than or equal to 2 power k. Like that's the only element. If there was anything, like you would also have 2 power k plus 1 in this set. That's what you can show. And we just assume k is the largest. So this is a unique element in the sum with the largest possible value of the norm. Everything has a norm smaller than this. But didn't we already see this, that if the norm of every element in a sum is less than some specific term in the sum, then the norm of the sum is equal to the norm of that largest element. So ultrametric inequality just shows that the p-adic norm of Hn is 2 power k. And as k is greater than or equal to 1, n greater than or equal to 2, that implies 2 power k is greater than or equal to 2. But wait a second, the p-adic integers contain the integers, and the p-adic integers were elements with norm less than or equal to 1. And this term has norm greater than or equal to 2. All integers are in Z2, which had norm less than or equal to 1. This is the p-adic norm over here. Hence, this term is not in the p-adic integers. Specifically, it's not in the integers, and thus Hn is not an integer. Fascinating, right? Just a 4-line proof of this. Anyway, the proof isn't hard, and you kind of use the same techniques. This is just a different language to say that. But what we have actually shown is way stronger. We have shown that Hn, the norm, is equal to like the largest power of 2 less than or equal to that. So that's the box of log 2n in some sense. And log 2n grows to infinity. So we have shown that Hn2, the p-adic norms of the harmonic sums, goes to infinity as n increases. That's fascinating. Like in real, it happened. In p-adic, it's happening. Now it is a conjecture. Yes, even though p-adics have been around for quite some time now, still not known till date whether given any prime p, h and p goes to infinity as n goes to infinity. For 2, we have established it. It is known for a few other primes, but after some time, like we just don't know anything. There is no generic technique to prove this. This is expressed by the following equivalent statement, which seems a bit more tractable. The statements over here that the Hns are p-adic integers for only finitely many indices. That's equivalent to saying this limit is infinity. That's also equivalent to saying that Hn is in p power k zp. That means like it's a multiple of a p-adic number by p power k. Like that's a product of these two things, and well, that's smaller. Like if k was 0, that's precisely the first thing. And this is the form in which they had reduced the conjecture to, and they thought they would be able to solve it from there. They couldn't. And they defined this JP object, which is the number of harmonic numbers greater than or equal to 2, such that it's in PZP. Then we have already established J2 is equal to empty. J2 is an empty set. One can show J3 has 3 elements, J5 has 3 elements, J7 has 13 elements, J11 has 168 elements, but still finite. And the theorem just says that if it's finite, then H and P goes to infinity. And thus you have H and P goes to infinity whenever P is less than or equal to 11. At least based on my searching, there has been some more improvement. Like we do know something about J13 and things now, I think, but it's still not known whether this sum converges. Observe that over here, 2 is in J3, 5 is in J4. We are not allowing 1, otherwise 1 was in J2. We are only considering greater than or equal to 2. That's the difference. So now we observe a pattern. 2 is in J3, 4 is in J5. In fact, had I written down J7, you'd realize 6 is in J7, and so on. So as a final remark, we state the Wollstone-Holmes theorem. You can prove the second part of the implication without the Wollstone-Holmes theorem, but it's an interesting result. If P greater than or equal to 5 is a prime, then HP minus 1 is in P square ZP. So at least P minus 1 is in JP, the thing which we were considering. So JP is always non-empty. That's an interesting thing. We wanted to show it's finite, but we ended up showing it's non-empty. Not bad, but yeah, kind of the opposite. If it was empty, it would have been better. The proof is actually straightforward, and you can do it simply like using some p-adic methods or modular arithmetic, but we skip it for the want of time. And it is also an interesting open problem to find all p such that P minus 1 is in P cube ZP instead of P square. Again, this problem has been around for quite some time, even before p-adics were used so heavily. Such primes are called the Wollstone-Holmes primes, and only 2 of them, both pretty large, unknown to date. And if anything else is there, it should be at least 10 power 11 or something. And we don't know any other whole primes as of now. And that's fascinating. The second application, which I'll quickly gloss over, is something called the Skolem-Mahler theorem. It's in algebra and combinatorics, namely in recurrence relations, something which you might have encountered while you were preparing for your Olympiads or preparing for your examination or limit examination for that matter, or just encountered it in some other subject, computer science or physics for that matter. Now consider an integer linear recurrence relation that is a recurrence relation of the form an equal to r1 an minus 1 plus dot 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 rk an minus k, where each k greater than or equal to 1, r1 to rk are fixed integers. They do not vary with your n or anything. And all the ans are integers, but they vary with n, of course. It's indexed by n. So for example, look at the Fibonacci recurrence or anything like the Lucas, like it's kind of the same thing, but you do have many other recurrence sequences. Even the factorial is technically a recurrence relation, but it's not an integer linear recurrence because R1 over there you'll have an is n times an minus 1, and n varies with like the coefficient of n minus 1 varies with every term, and we don't want that. We want these to be independent. So what can we say about the set of integers n such that an is equal to 0? That's the question we are interested in. It can very well be finite. The Fibonacci has no 0 terms after like a0 in some conventions, but we are only considering a1, a2, and so on and so forth usually. But even if like Fibonacci is considered a0 equal to 0, like, that's also just one term. And you could also do this construction which says that a0 to ak minus 1 is 0, and anything after that is non-zero. Just take the sum till the kth step in some sense. And you can do other constructions and show that it might be infinite as well. Say for instance, a1 and a2 are 0, a3 is 1, and you define an plus 3 is equal to 2 times an. So a4, a5 are again 0, a6 is 2, so on and so forth. You can also combine these two in a clever way, and it can be a union of this, a finite set and a finite union of APs. Over here, you had infinite APs, like it's 1 plus 3k and 2 plus 3k in some sense. So you can do some clever combination and you can get those two things as well. But can it be something else? Say z is equal to the squares. Like, okay, z over here is the set of zeros. So we have shown it can be a finite union of APs. It can be a finite element. Can it be anything else? The surprising answer is no. And that's the Skolem-Mahler theorem, which says that given any integer linear recurrence defined as above, z is a finite union of APs, possibly constant ones. By constant ones, I mean it's a finite union of a set, a finite union of a finite set, and a few non-constant APs. So actually, the theorem is a bit stronger than that. These APs, the non-constant APs, should have a common GCD. Can actually prove that. Sorry, common difference. CCD. Okay. Anyway, so interestingly, all known proofs of this theorem rely on p-adic techniques. I do sketch a proof later, but I'll skip it now because I want to talk about the next one. What's interesting is that even though p-adic techniques give us a proof of the Skolem-Mahler theorem, there is no effective way to determine finiteness or existence of zeros. By effective, I mean there is a way a computer can determine whether, given the data of, say, what A1 to AK is and what the linear recurrence is, can the computer determine whether this has finitely many zeros? The unfortunate answer is no. Like the ones we had given, of course, we can determine it, but if it was an arbitrary sequence, we do not have a lot of control over it. And the p-adic method just says how the set of zeros look like. Well, it says a finite then APs. So it might happen it's finite, because we can only check till a finite time. And then the APs start very late. Or there are no APs after all. There are just finitely many zeros. There are no effective methods to determine it till date. Of course, a lot of research is being done on that, but we do not have anything really about this finiteness, like an effective way to determine finiteness. Of course, linear recurrences occur in computer science and they can only talk about things which are finite in some sense. So they are interested to know about the effective finiteness of this thing. So the final application which I'll talk about today in the next few minutes is Monsky's theorem. And for those who got a bit bored by the computer science and linear recurrence talk, or perhaps the harmonic sum and analysis part, this is something which is fascinating and easy to describe at least. Given a square and an integer n greater than or equal to 1, can you divide the square into n triangles of equal area? So I guess most of you know what a triangulation is. Division of something into triangles, surface, or anything for that matter. And squares are kind of plane surfaces, so you can talk about triangulation of squares. So can you divide the square into n triangles of equal area? So before I proceed further, quick question. Can you do it? Can you divide it into 2 triangles of equal area?
Yes.
Yes.
Yeah.
Diagonal.
Yeah, you can.
Along the diagonal.
4?
Yes, sir.
Yeah.
Considering both the diagonals.
Both the diagonals.
Both.
in your-
6? Need some thinking over here.
Yes, sir.
Okay, yes. So who said yes?
Oh, sorry. No, maybe not.
No, it's fine. Like I see that most of the responses over here are no,
I
but
thought, yeah, I
it is
forgot
yes.
about the equal area.
No. The answer is yes. You can divide it into 6 triangles of
I
equal area.
think maybe we can take a diagonal and then
Yeah.
try to the triangle that we get formed, we can try to dissect it.
Exactly. That's what you do. Or you can just break the square into 3 rectangles of equal area. You can do that, like parallel rectangles of equal area, and then use diagonals in each of them. That's fine as well. So using these tricks, you can actually show whatever you suggested. It's brilliant. And using that, given any even integer, you can dissect it into like if n is even, you can dissect it into n triangles of equal area. Now, what about 3? 1, of course, the answer is trivially false, so we would not look at that. 3. Okay, without wasting more time, because we do have to finish in a few minutes. How much time do I have, Sunshine?
You have 1 more minute left, but it's okay. You can go for 15 minutes.
Okay, sure. Give me 5 more minutes and I'll try to wrap it up. At first sight, the answer always seems to be yes, because, well, you can divide, you can form triangles of those areas, but the fitting part is the hard thing into a square. And the n equal to 2k case is fairly easy, as we have discussed. The first major block is n equal to 3. In fact, we'll talk about it as well, that you cannot do it for n equal to 3 in a direct way. But what was a open question by Richmond for 5 years and finally proved by Monsky is that such a triangulation is called an equiareal triangulation because the areas are equal. It is possible if and only if n is even. So now for the rest of the talk, next few minutes, I will share the screen over here. Okay, is my screen visible, guys?
Yes, sir.
Okay, so Monsky's theorem, if a square admits an equiareal triangulation, then number of triangles is even. Okay, let's first quickly do the n equal to 3 case, because I promised you that. So how many more vertices can occur over there? So if this is a square, say, of course, not a very well-drawn square, but let's assume it is. Can it, of course, like you cannot just use these vertices to get a 3 triangulation. You would need at least 1 more vertex. You can actually show that. And now if that vertex is over here, then you would have to join these because it's triangulation. And hence you would have at least 4 triangles and you need 3. So that's not allowed. So the only other possibility is this point is over here, or like one of the edges. And you can actually show that this is the only way in which you have another triangulation, or, well, there is another way. And that's exactly not a triangulation in which I'm interested, but of course, even that one you can show there is some problem. It's like something like this, like joining this 3, and then you're saying, okay, that's a triangulation. But in either case, these are not equireal. And you can actually verify that you cannot get an equireal triangulation if n is equal to 3 using techniques similar to this. But now, for the rest of whatever time I have left, I'll talk about this. The proof using p-adics as to like whatever Monsky's proof was, it was kind of the same as this, that you cannot get p-adic triangulations. So I've tried to color code it as much as possible, and that's why I've shifted to writing. So the ingredients are p-adic norms. There is a p-adic, two-adic, like in our case, p is 2. So p equal to 2 over here. There is a two-adic norm on R, which extends the two-adic norm on Q. So this is just the restriction sign. And so it has these properties. The most interesting one is the triangle inequality and the property of like what are the values on Q. And of course, the product rule. The second ingredient which goes into the proof is something called Sperner's lemma. I think some of you might have encountered it in combinatorics, not in this domain, perhaps. And it is a very beautiful statement. It says that P be a convex polygon, and suppose its vertices are colored red, blue, or green. Consider a triangulation of P and color all the vertices of the triangles involved by red, blue, or green, like a good triangulation, like the one over here. And hence, like as I was saying, like I'm not interested in something like this, because then this the thing on the right is not exactly a triangle. It's more like a degenerate quadrilateral where two sides are kind of parallel to each other. Two adjacent sides are parallel to each other. So I won't call it a triangulation. But at least this is a triangulation, and the one which has been drawn over here. And you're painting every vertex, either red, blue, or green. Let RB be the number of red, blue edges on the boundary. So precisely in the diagram, they are the ones over here, this one, and this one. So RB is equal to 3. Let BG be the number of green, blue edges. So that is precisely this one. So it's just 1. And finally, the red RG is the red, green ones. So it's this one, and this one. Of course, there are blue, blue ones or green, green ones, and we are not interested in those. We are just looking at smaller edges. And finally, let X be the number of RBG triangles in the triangulation. By an RBG triangle, I mean a subtriangle in which every vertex has a different color. And that is precisely the ones with the dots inside. So you have 3 of them. So maybe all of them are not equal. Some of them coincidentally are, but they might not be equal. But what Monsky's theorem says is that what Sperner's lemma says is that these 4 things have the same parity. By parity, I mean either all of them are odd simultaneously or they are even simultaneously. So now we might not talk about the proof of Sperner's lemma. I'll share this document as well. You can have a look later on. It's very simple, like it's just this much. The proof is just this. But we'll not talk about it. We'll talk about the proof of Monsky's theorem using this. So instead of proving it for an arbitrary square, we can just look at the specific square, right? The unit square 0, 0, 1, 0, 1, 1, 1, 0, 1. If you can prove it over there, you can just change any square, dilate it, and like move it around to come to this square on the argument plane, and we're done. So now we give a specific coloring of the square. I'll color, like you look at a triangulation of that thing and then color the points to be red if both of them have p-adic norm less than 1, to be green if the p-adic norm of y is greater than or equal to 1 and it's also greater than or equal to the p-adic norm of x2, and blue if x has a p-adic norm greater than or equal to 1 and that has a norm greater than the p-adic norm of y. You can verify that these are an exhaustive set of colorings. Now, any RG edge can only occur on the side ON. Like over here, as you can see, N is green, M is green, L is blue, and O is red. Sorry. And on NM, for instance, you cannot have a red point, because any point over here looks like x comma 1, and 1 has a two-adic norm equal to 1, and that's not allowed. For red, you have to have two-adic norm less than 1. And similarly, you cannot have a red one on LM, no red, so no red, no red. And in this one, no green is possible. Because for a green one, you need to have mod x to, sorry, the mod y to greater than equal to 1. And over here, the mod is 0, like it's just any point is of the form x comma 0. So mod y2 is equal to 0. That's not allowed. Okay, so you have a coloring now. Now that you have a coloring, and now anything occurs over here, one is red, one is green. So you can have red, green. But can you show, like it's not very hard to show this, that the number of red, green edges has to be odd? Because it's kind of like, if you collapse the ones which have the same color into one point, like of course that affects the triangulation, but just for counting purposes, then it's kind of an alternating sequence of red, green, red, green, red, green. And that means there are just odd many edges. You can actually verify that. So by Sperner's lemma, x, the number of RBG triangles, should be odd. At least because it's odd, it is not 0. 0 is even, hence it's not 0. So there is an RBG triangle in the triangulation. That is the only place where you need Sperner's lemma. And let UVW be an RBG triangle. Some arithmetic goes through, not very hard. Just use the way the coloring has been defined to show that the area of an RBG triangle, using some coordinate arithmetic and all those things, some coordinate geometry over here, you can actually show that the area is greater than or equal to 2. I'll leave it as an exercise to you, or as I said, I'll share these notes so you can have a look at it later on. But let's assume this for a while. Anyway, it's not very hard. And use it to show that the number of triangles in the triangulation, call that k, is even. So now area of the square is 1, which is k times the area A. So you have ka is equal to 1. So if you take the two-adic norms, that is equal to the two-adic norm of 1, which is 1. So the two-adic norm of k times the two-adic norm of A is equal to 1. Over here, we know that the two-adic norm of A is greater than or equal to 2. So this is greater than or equal to 2 times the two-adic norm of k. That implies the two-adic norm is less than or equal to half. But that precisely implies k is even. For odd numbers, the two-adic norm is 1. Like there's no power of 2 dividing it. So 2 power minus VPN is 2 power 0, that's 1. And if it's even, then it is less than or equal to this. So this is how you can use two-adics to prove something fascinating. Now you might think that, okay, in the harmonic case, we had some techniques to talk about this without the p-adic technique. Like you may use the p-adic, you may not. Surprisingly, just like the Skolem-Mahler theorem, Monsky's theorem, there are a few variants of this proof, but all of these proofs rely heavily on the existence of a two-adic norm on R. There are no proofs without p-adic techniques. Okay, so now returning to the presentation for a while. I'm sorry for the last few minutes. Resume presenting. Okay. So now we have a proof, and you can actually do the basic cases by yourself, like 3. And the funny thing is, like, a computer would have told you the answer is yes. Like you can always have a triangulation with n greater than or equal to 5, because computers can only approximate stuff, and you can get any degree of approximation for n greater than or equal to 5. It's possible. Anyway, we'll not talk about that. Now, with this being settled, here are a few generalizations of Monsky's theorem. Instead of starting with a square, you could have started with any n-dimensional parallelepiped. So for 2 dimension, it would have been any parallelogram for that matter. And you could have shown that if you want to divide it into equal volume divisions of generalization of triangles being n simplices, if you don't know it, it's fine. I've defined it over here, but okay, it's not important. if and only if n factorial divides k. Of course, this proof is way, way harder than this thing and way beyond the scope. And it uses, of course, it uses p-adic techniques, but not as simply as this one. It uses in a very complicated fashion. And any regular n-gun with n greater than or equal to 5 admits, sorry, it's an equiareal triangulation with k triangles if and only if n divides k. Sorry. Okay, yeah, that seems to be fine. Okay, and there might be a typo. I'll just have a look at it later on. And any central symmetric polygon or a polymino, like that's kind of like a domino, but you, instead of just taking 2 blocks, 2 cross 1, it's like a pasting, like you keep on pasting squares, unit squares. That does not admit an odd equiareal triangulation. So these are 3 kind of generalizations or variants of Monsky's theorem. All 3 of them are way harder proofs, but maybe the statement of the 2 needs a bit of check, but I think it's fine. And here are a few references for the p-adic numbers if you are interested to follow up on this. Of course, I had to rush through a lot of things. They are more interesting when once done carefully. So needless to say, there is this crazy world and interesting world of p-adic numbers that not only destroys our intuition completely, where infinity becomes -1 to Ullmann, and also has a plethora of neat applications which needs to be explored. And there are a lot of open questions over there, way more than you have. A lot of accessible open questions over here, in the sense that you can state them easily, because it's at the end of the day number theory. And to paraphrase the famous mathematician Kazuo Kato, the real numbers like the sun fill our vision in the day, but at night, the p-adics, like the stars, come out and shed new light. Of course, before I go further, one last statement. P-adics have been heavily used in a lot of results, including, not limited to, of course, but the much celebrated proof of Fermat's last theorem. It's heavily dependent on p-adic numbers. And a lot of other number theoretic things, whatever is known, like most of the results which are used these days and which have been proved after a lot of effort are heavily reliant on p-adic techniques. So thank you so much for your attention, and sorry for rushing towards the end, but I hope you had a glimpse of why p-adic numbers are important. So if you
Thanks. Yeah, thanks for the wonderful talk. I hope everyone enjoyed. I can see a lot of claps. Anyway, if you have any more questions, please feel free to unmute yourselves and ask the speaker.
Yeah. Okay, someone raised their hand. Please go ahead. You most welcome, Neelab. So if you have any questions, feel free to ask. Of course, no, I'm not Australian, I'm Indian completely.
Well, wait for 2 minutes. Let's see if then.
For the notes, surely I'll be sharing them with Sunshine. Recording, I don't know what the policy of limit is. So
Yes, was it okay for you to share the recordings?
Okay,
Or
let's
might
talk about it later. Yep. At
Yeah.
least the notes, you'll have it soon. Definitely.
Yeah.
I'm so glad to know that all of you had fun. And well, once again, congratulations for qualifying, and have fun with. How many days of the camp are left, Sunshine?
2 more days. Yeah.
Okay, so have fun with the rest of the month. I'm sure they'll be awesome as well. So Australia University. Oh, I am a student over here. I'm doing my PhD at Australian National University.
Okay, there should be no more questions. Then. Okay. Oh, there is one.
Okay, there was one question. Yep.
Yeah.
I have read about. every point in a circle is the same distance from the boundary. Okay, I don't exactly understand what you mean by that, but
Maybe Anand can unmute yourself and ask.
yeah.
So I was reading about p-adic numbers and the geometry, non-trivial geometry related to that. So it came up as a fact, but it was no proof was provided that every in ZV in QP the Q space QP
Mhm.
any circle and any interior point of a circle is equidistant from the boundary point, not only
Okay.
the center point.
Okay, with respect to p-adic, yep, that makes sense. Because
With respect to the p-adic norm.
yeah, exactly. So the idea is simple. Like the way we did it is like if something is smaller, then the two larger things should the other two should agree and be the larger than that, right? Like if some A was lesser than B, then C was equal to B. Like that's what we kind of proved, right? And then just keep on doing this repeatedly. In some sense.
And can you please elaborate on the point in the previous point you highlighted about it being a discontinuous, oh sorry, disconnected space?
Okay, so a totally disconnected space is something where like you do not have any like anything. Of course, single points are connected. You know what a connected space is?
Yeah.
Yep. So anything other than that is not connected in some sense. So that's what we call totally disconnected. In ZP, that's the case. Like like if you give me any other non-trivial set, you can show it's disconnected in some sense.
But it's only for the ZP, right? Not for the extensions into complex.
Actually, it is still valid over there. Like any extension, also you can show that that cannot be connected. There are some complex. Okay, I'm so sorry. Like complex, yeah. In complex, yep. There are some instances, but wait a second. I'm just thinking about it. No, I think even that one is totally disconnected. I'm not sure about that, but I think so. Because in the complex one, the p-adic norms takes values p power q, where q is a rational number. Rationals are still discrete. Like you use basically in the proof of this, you use some properties. Over there, you do have some differences, like the open balls might not be closed always, but I think still there are some like no non-trivial thing can be connected in that case. I'm not sure. I'll just get back to you. Like maybe I'll convey it to Sanjay and I'll have a look and convey it. Or maybe you can also search it up on the internet.
Okay.
At least it is not connected. That's for sure. Okay, sure. And guys, I think it's time for your next session. So we should wrap it up. Thank you so much for your attention, and it was a pleasure. Bye-bye.